Today we're going to learn about dilations and reflections. For a vertical stretch or compression, we have g of x is equal to a times f of x. And for a horizontal stretch or compression, we have g of x is equal to f of, in parentheses, a times x. Now on the vertical side, if a is greater than 1, then we're going to have a stretch. If a is between 0 and 1, then we're going to have a compression. And on the horizontal, if a is greater than 1, we're going to have a compression. And if a is in between 0 and 1, we're going to have a stretch. So let's graph these three functions here. We have g of s is equal to f of, in parentheses, 2 times x. We see that this is a horizontal dilation. A dilation being either stretch or compression. Now, for the horizontal here, the value of a is 2, and that is greater than 1. So we know it's a horizontal compression. So a compression means that the graph is going to shrink in the horizontal direction. So instead of looking like this parent function here, it's going to look something more like this, perhaps. Now, we're going to base all of these functions on the parent function, f of x is equal to x. And the parent function is already on this graph here. So a horizontal compression of 2 would mean that the slope of the line is 2. So unlike the parent function with the slope of 1, for each value in x, we're going to have a value in y that's 2. So when x is 1, y is 2. When x is 2, y is 4. Like this. And sure enough, our line is going to look like this. This is a horizontal compression. The line's margins from left to right appear to be more compressed. And how about this next function here? We see that this one is a vertical dilation because we're multiplying 0.5 to the function f of x after it's been evaluated. So this is a vertical dilation, and the value of a is in between 0 and 1. So we're going to have a vertical compression. Vertical meaning up and down. So this means that the vertical distance is going to be less. So instead of the distance of the parent function, which is like this, maybe the new function is going to be a little shorter like this. The vertical distance, at least, of the function. Now, because the function is 0.5 times f of x, the slope of the line, based on the parent function, is going to be 0.5. Because the parent function f of x is equal to x, h of x is essentially 0.5x. So the slope is 0.5. So that means for every 2 in the x direction, we're going to have a point of 1 on the y. So the graph is going to follow the points here. And sure enough, the line looks something like this. This is h of x. How about this last function? P of x is equal to 0.5 times f of negative 2 times x. We see that this is a vertical and horizontal dilation. So on the vertical end, we have 0.5, which means it's going to be compression. On the horizontal end, we also have a compression, if the 2 was a negative. Now, one thing to note about both vertical and horizontal dilations is that if there's a negative number involved, the graph is going to be reflected. What does reflected mean? Well, if we had the parent function f of x equals x, and we were to flip it so it's f of x is equal to negative x, then instead of the parent function of this gray line having a slope of 1, the slope would be negative 1, and the graph would look something like this. Now, the thing about this last function is we can use the parent function f of x to simplify the expression. P of x is equal to 0.5 times f of negative 2 times f of x. Now, f of negative 2 is, if we plugged in negative 2 for x, we'd get negative 2. So f of negative 2 is negative 2. So we're going to have negative 2. And f of x is equal to x. So we're going to have x. So p of x is going to be 0.5 times negative 2, which is negative 1, times x. Which means p of x is actually equal to negative x. So instead of the parent function, the slope of the line is just reflected across the x-axis. And we're going to see that the function p of x looks like this. It's the same as the parent function, just reflected. Now in all these cases, I use the parent function as f of x. f of x can change depending on the problem you're trying to solve. But you can always utilize what value you're given for f of x to simplify your expression, like I did in this third problem.